So again, right, the setting for partial derivatives is that whenever you're differentiating with respect to a specific variable, every other variable just gets to pretend to be a constant. So what I'm going to show you one thing that's very kind of basic, and then we'll just do a whole bunch of problems. So for example, now, so these shoes are totally in the way. Sorry. Move it, shoes. All right. So let's say I had a function. Let's say my function f of xy was x to the fourth y cubed plus y e to the x squared. So here's what I actually imagine when I'm doing this. If I say, if I want to find the partial with respect to x, what I'm really doing, and I'm not actually going to, so I'll write stuff, what I'm really kind of thinking of is, okay, if I'm doing the partial with respect to x, I'm thinking of y as a constant. I might say y is equal to 1. So I can say, well, my function, right, f of x comma 1, well, let's do 2. 2 is a little more interesting. F of x2 would be x to the fourth times 2 cubed plus 2e to the x squared. And if I were to differentiate that, well, the derivative of 8 times x to the fourth is 8 times 4x cubed, or 4x cubed times 2 cubed. And the derivative of 2 times e to the x squared is 2 times e to the stuff times the derivative of the stuff. So what I'm actually doing is I'm pretending that y is 2 for a minute, but then I'm remembering that when I actually do this, y has to be y, not 2. So I'm like, oh, that's really 4x cubed times y cubed plus y times e to the x squared times 2x. So when I differentiate this, right, I'm just saying, okay, that's a constant multiple. My derivative is 4x cubed y cubed plus y times the derivative of the x squared is e to the x squared times the derivative stuff. And then we can flip it and do the same thing, but now we're taking the partial with respect to y, which we could also write as del f del y. Now we're holding x constant. Sorry, so the variable you were differentiating with respect to is the one that's changing. The other variable or variables plural, if there's more than one other one, are all acting like constants. So the reason I plugged y, so that's not something you will see people do generally in Max, but the reason I did it was just to kind of emphasize that y is acting like a constant. So right here, I'm looking at the function, I'm really saying, okay, I'm just going to let y be a constant for me. And then I said, okay, y is this constant too? And then I took the derivative of that expression when y was equal to 2, and I got this expression here. But then really, we're saying, well, that's true no matter what constant you're letting y be. Y could always be 2, y could always be 3, y could always be 7. So instead of picking a particular value, we're just saying when we do this, we know that y is some particular value, some constant value, right? Y isn't changing. And then we're asking what the derivative with respect to x is. So you don't usually do this. I was just doing it to kind of make the point extra clear. Although hopefully it sounds like it might have made it a little less extra clear. Hopefully we've clarified things now. So now in this case, we're doing the same thing, but now we're holding x constant. We're just pretending that x is a constant. Right? We know that in life, x is a variable, but in this constant, when you're talking about this partial derivative, you're saying, oh, we are only moving in the y direction. So x is actually acting like a constant. Right? If you have, and this is where my drawing skills are going to be kind of weak. If you have some surface, say, let's pretend James can draw. So we have some surface, right? We've got like some contour line like this. If we're moving in the y direction, right, we're moving this way. There's like maybe moving in the x direction, right? But we're basically saying if we're moving along this contour line, that's probably not the best. If I'm moving along this line on the surface, I'm moving in the y direction. The x value isn't changing, right? I'm at some set x value. So the partial with respect to y is just going to be whatever the slope is in the y direction. So here, right, I'm pretending I'm holding x constant. So 4x cubed is a constant multiple. Not the derivative of this. Sorry, the derivative of this. The derivative of x to the fourth times y cubed is going to be x to the fourth times 3y y squared. And the derivative of y times e to the x squared is going to be 1 times e to the x squared. We can also find the second partials. Erasers. I hid my eraser. I was cleaning my board earlier and I moved stuff around. Sorry. So we can find fxx, which is the partial with respect to x of the derivative of the function with respect to x, or the partial with respect to x. Okay, so it's the derivative with respect to x of the derivative with respect to x. So we're taking the derivative of this with respect to x. So it's del x of 4x cubed y cubed plus y times e to the x squared times 2x. This is going to get a little bit messy. So the first part's not so bad. The partial derivative with respect to x here is going to be 12x squared times the constant y cubed. Now the derivative, the partial derivative with respect to x of this part here, we have a y, which is a constant, but then we have an e to the x squared times a 2x. We have two different instances of our variable multiplied together. We're going to have to use the product rule. So we're going to get plus y times, I'm going to think of this as a product, right? I can think of this as g and this as h. So then the derivative is going to be, okay, the derivative of the first thing, which is e to the x squared times 2x, times the second thing, which is 2x. Right, so it's a g prime times h, plus then we want g times h prime. So e to the x squared times 2. And there's your second partial derivative with respect to x. And I'm running out of room, that's okay. Let's do the y, the second partial with respect to y over here. So I want to find fyy, or del squared f del y squared. We are going to just take the derivative with respect to y already and differentiate with respect to y again. So here, so in fact, let's write it this way. It's going to write it as the partial with respect to y of the derivative with respect to y. So that's going to be, I'm going to rewrite this just a tiny bit. I'm going to write it as 3x to the fourth y squared plus e to the x squared. This is actually going to be much easier. So again, we're treating y like a variable and x like a constant. So I have a constant times y squared. The derivative is going to be the constant times 2y. I have a constant, right? E to the x squared. There's no y's in there. Y is my variable. X is a constant. That's a constant. How exciting. Let's also talk about the mixed partials, which I know he was, so these second derivatives, fxx and fyy, tell us about the concavity of your surface, whereas fxy and fyx, the mixed partials, tell us about kind of like the twist is what he was saying, where you're kind of saying, okay, you're talking about the change in one direction, but then you're going in the other direction. So it's not, I don't have a really good interpretation of how to describe it exactly. And I had to cut out of class halfway through, so I didn't see, I was leaving like right as he was talking about that. So I didn't see what else he had to say about it. But it kind of tells us, it has to do with telling us about whether or not we have a saddle or something else. So let's go ahead and find the mixed partials. So something to be aware, so actually something that matters and then doesn't. Why does it move from the y to the x to the fourth? Well, because, so Catherine, the reason I moved the 3 around is because usually we like to write constants, meaning the actual constants, not the x or y that's pretending to be a constant. Usually I like to write constants in front. And since it doesn't matter what order we multiply things in, I'm going to write the 3 as 3 times x to the fourth times y squared, instead of as x to the fourth times 3 times y squared. Just a matter of convenience, really. We can always rearrange the order of multiplication to whatever suits our preference. So something to be aware of that both is and is not an important. So if you write fxy, it means first you do the derivative with respect to x, then you do the derivative with respect to y. And in the Leibniz notation, that's going to be del squared f del y del x, right? Because this is first you do del f del x, and then you take the derivative of that with respect to y. The thing that's confusing a little bit about this is that the order is the opposite, right? Here the order is x first and y first. Here the order is y first and x first if you read from left to right. But I want to make sure everybody's super duper clear about this. When you write this derivative this way or this way, we actually read it from right to left. Because you're saying first you do this derivative to your function, and then you do this derivative to that result. In actuality, it doesn't matter a whole lot because it ends up being the case that for all the functions we're going to interact with, fxy and fyx end up being the same. Now, it does matter, and it probably will matter to your professor because it is important that you think of it the right way, right? If he says write this and you show him you do it in the opposite order, he might have a small issue with that. So you should try and do it the right way, but just be aware that if you accidentally mess it up, you'll still probably get the right answer. So let's go define this. So fxy, I'm taking the derivative of this with respect to y. So this 4x cubed is going to be a constant. So I'm going to get that constant times the derivative of y cubed, which is 3y squared, plus the derivative of this with respect to y. So I've got y times a big old constant. Well, the derivative of y times a constant is just 1 times the constant. So there's my fxy. Or my del squared f del y del x. We could also check and see that fyx, which is first doing y and then doing x, I should really say first doing the partial derivative with respect to y and then doing the partial derivative with respect to x. That's going to get us, well, if we take the partial derivative with respect to this, sorry, the partial derivative of this with respect to x, I've got x to the 4th times this constant. So the derivative is going to be 4x cubed times that constant. And the derivative of this is a function of x. The derivative of e to the x squared is e to the x squared times the derivative of x squared. And look, they're exactly the same. So we can expect all the time for those to be the same, which is nice, right? It's less of a hassle. Let's do a little more practice. Sometimes things can be pretty gross. Let's look at, let's see, sure, yeah, definitely, Max. So if you, so it's really about notation, right? If you write it this way, it means your first differentiate with respect to x, second differentiate with respect to y. And we write that in this notation that way, but in the Leibniz notation, we write it this way. Which means del del y of del f del x. Or we could even space it out even more as del del y of del del x of the function f of x, y. So first you're doing the partial with respect to x, and then you're doing the partial of that with respect to y. So when you write the notation this way, you read from right to left. You say, oh, first I do that derivative, then I apply that derivative. When you use this kind of less bulky notation, the order happens to be switched because we read this one from left to right and say, oh, first you differentiate with respect to x, then you differentiate with respect to y. Yeah. So let's look at a couple more examples. Let's say, sure, let's look at an easier one just to kind of make sure we're all really kind of on board with this. Let's say our function f of x comma y was equal to, what have I got here? X to the 7th plus y to the 5th plus x squared y cubed. And I want to find all 6 derivatives, all 6 first and second derivatives. So the 2 first partial derivatives and the 4 second derivatives, meaning fxx, fyy, and the two mixed partials. This one's a little bit easier than the previous one. So I like to use this notation just because it's more compact, right? There's less writing to do there. But we can totally write del f del x if you prefer. And do notice, right, it is a del, right? Not the singer. It's the letter del with a curly d. So the partial with respect to x is going to be 7x to the 6th. The derivative of y to the 5th is 0 with respect to x. And the derivative of x squared y cubed is going to be 2x times y cubed. The partial with respect to y, which is del f del y, is going to be, let's see, derivative of x to the 7th is 0. Derivative of y to the 5th is 5y to the 4th. Derivative of x squared y cubed is going to be x squared times 3y squared. And now you can simplify that a little bit, right? You could totally, you should rewrite this as 7x to the 6th plus 2xy cubed. We should write this as 5x, so 5y to the 4th plus, I would write this as 3x squared y squared because we like to put the constants in the front. And then our fxx is going to be, so we just take our fx and we differentiate with respect to x again. So we get, let's see, 42x to the 5th and 2y cubed. And then fyy, differentiate this with respect to y again. We're going to get 20y to the 4th. And then we're going to get x squared times 6y. Which again, I would write as 6x squared y. And then finally, the mixed partials. Something we're saying mixed martial arts. We're doing mixed partial arts. Kind of. Maybe. That doesn't work. Mixed partials? Mixed partial arts. I kind of like it. Anyway. My jokes are not good. It's all right. fxy, we're taking the derivative with respect to y now. So we're looking at fx first and then differentiating with respect to y. So we get, let's see, derivative of 7x to the 6th is 0. Derivative, I mean the 0 is gone, right? And the derivative of 2xy cubed is going to be 2x times 3y squared. And then we hope, right? So here's a good check. If you do the mixed partials both ways, not that you're going to probably, like I did one, I know the other one's the same. But if you're unsure, maybe you're like, maybe I made mistakes and whatever, you can check the mixed partials. And if you did things right, they should come out to be the same. I mean, they definitely should come out to be the same. Unless you've got some weird piecewise defined function that is funky. So fyx, we take the derivative of this with respect to x. Derivative of 5y to the 4th is 0. And the derivative of x squared 3y squared with respect to x is going to be 2x times 3y squared. Check. Check. Let's do one more, and then we will talk. I mean, actually, maybe not. So, I mean, really, you've definitely. What I want to say here. What I want to say is, if you're a confident differentiator, right? If you know how to do your derivatives well, partial derivatives really aren't anything new, or really, once you kind of get your mind locked around it, they aren't that challenging. You're like, oh, I'm just pretending like this one variable is a constant. And then the other thing is just a function of one variable. And we know how to differentiate functions of one variable. So I really want to stress, if you just practice these partial derivatives a little bit, you'd be like, oh, I've got this, right? I know how to differentiate things. I'm just pretending like this other variable is a constant. Let's do one more function of two variables, and we will. Let's see. Let's say f of x comma y is x squared over x cubed plus y squared. Might be a little less nice than I intended to be, but that's all right. So let's do all things. I'll use the other notation this time. Let's find del f del x, which is going to be, so the bottom times the derivative of the top times the top. Oops, the top is x squared times the derivative of the bottom, which is 3x squared plus y, whoops, plus 0 all divided by the denominator squared. I think I've made my life unnecessarily challenging here by making this a little, yeah. I'm just debating if I really want this to be as hard as I've made it. No, I really don't. Yeah, I'm gonna change this just a little bit because the example that I've modified is really better if I don't modify it. So let's do this one instead because our results will come out to be just a little bit nicer. So let's say we've got this function. F of xy equals x over x plus y. Let's find the partials. So del f del x, the bottom times the derivative of the top minus the top times the derivative of the bottom, which is 1 plus 0 divided by the denominator squared. Now, since we know we're going to be taking the second partial derivatives, it's in our interest to simplify the first derivatives. So notably, this is x plus y minus x on top, which is just y over x plus y squared. So yeah, if you know or think you might need to take the second derivative or further derivatives, you usually want to spend the second or two to simplify your first derivative. Especially if it's one that's not too terrible like this. Let's find del f del y. So del f del y is going to be, again, bottom times the derivative of the top. But now the derivative of the top is 0 because the top is a constant. Minus the top times the derivative of the bottom, which is 0 plus 1. Right, derivative of x is 0, derivative of y is 1. And then the bottom squared again. So this ends up being 0 minus x, so negative x over x plus y squared. Okay, now the second derivatives, which are going to be kind of gnarly. Del squared f del x squared. So when you do write this notation, if you do write it this way, just be aware, right? On top, the square comes between the del and the f, and on the bottom, the square comes after the x. So that's going to be, so we're going to differentiate this. In fact, you can get it right. It's going to be, sorry, we're going to differentiate that. Ooh, careful with the names. It's going to be del x of our del f del x. Okay, so we get, let's see, the bottom. So let's actually be a little bit thoughtful here. I know it's going to be the bottom times the derivative of the top. I know the derivative of the top is 0. So I'm going to get 0. Okay, well, that's not going to do anything. Minus, so we minus in front of the whole next part. So bottom derivative of the top minus the top times the derivative of the bottom. The derivative of the bottom is 2 times x plus y to the first times 1 plus 0. I wonder, yeah, in fact, for the next one, I think I'm going to do something slightly different. Yeah, there's an easier way to do this. That's all right that I didn't do it that way. And then the bottom is going to be, well, the bottom squared. Now notice here, what I really got is 2y times x plus y over x plus y to the fourth. And I can cancel one of those there and one of those there. So I end up with 2y over x plus y cubed. Now, what I should have done is what I'm going to do for the next one. If I'm going to find del squared f del y squared, it's del y, right, of del f del y, which is negative x over x plus y squared. Since x is a constant, this is the only thing that's really functional. It would really probably be in my interest to write this as the derivative of negative x times x plus y to the negative second. So look, I have a constant multiple of a function. I don't need to use the quotient rule here, right? I can say the derivative is going to be this constant multiple, and then the derivative of this function is going to be, well, the negative 2 comes down, and I get negative 2 times my stuff to the 1 less power, which is negative 3, times the derivative of my stuff, which is 0 plus 1. I'm not going to write that because we know that 0 plus 1 is 1, and times it by 1 is the same. So here we get 2x times x plus y to the negative third, or preferably, maybe not, I don't know. I prefer 2x over x plus y cubed. Very, very similar answer to the previous one. So that's probably a better way to do it, right? If you notice that your top part of your quotient is a constant because you're differentiating with respect to the other variable, then you can bring the stuff at the bottom up to the top and just kind of use, oh, I've got other things we do. I suppose we should find the mixed partials, which of course I've run out of room for. So let's go ahead and find let's find the following. Let's find, where'd you go here? So I'm going to find del squared f del y del x, which is the partial with respect to y of del f del x, which is the partial with respect to y of this del f del x, which is y over x plus y squared. And yeah, sure. So this one I am going to use the question here because the top and bottom both do have functions of my variable, pieces of my variable. So it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, which is 2 times x plus y to the first times 0 plus 1 over the bottom squared. Now in this particular case, I can factor out an x plus y on top. I've got an x plus, so let me actually simplify this a little bit. I've got x plus y squared minus 2y times x plus y over x plus y to the fourth. Each of these pieces on top have an x plus y, so I can factor it out. I'm left with an x plus y there minus a 2y there over x plus y to the fourth. And then I'm going to get x plus, an x plus y cancels. And I get x minus y, right? Because x plus y minus 2y is x minus y over x plus y cubed. And I'm not going to do the last one, but I do want to say, I think it would be in everybody's best interest to take a minute after class and to check to see if del squared f del x del y, which is del x of del f del y, which is the derivative with respect to x of our del f del y, which was negative x over x plus y squared. All of you should take a couple minutes and calculate this and see that you do in fact get the same thing. If you do get the same thing, you should check. Okay, let's see. I should talk about tangent planes for a little bit. So, again, I didn't see most of what he said, so I might be repeating some of it. It's all right. The idea of a tangent plane is literally the same idea as the idea of a tangent line, just with an extra dimension added in. So, for example, in 17a, we probably at some point found the linearization of some function. So actually, let me talk about, right, if I want to find, so let me see, yeah, sure. So I want to find, say, the equation of the line tangent to the function y equals f of x at the point, I'm going to be very general, let's say x naught, y naught, I think that's how we usually do it in class. The equation we use, or one way of writing it, oh, it's y minus y naught equal to f prime of x naught times x minus x naught. And this is the point slope form, right, where your point is x naught, y naught, and it's y minus y naught, x minus x naught, and then times the slope, which is the derivative at the point. And then you can solve for y. Right, so you can isolate y and say y equals y naught plus f prime of x naught times x minus x naught. And then you might remember, I don't know, there was also this linearization formula. The linearization linearization of a function f of x at the point, say, a comma f of a was given by the following equation. L of x equals f of a plus f prime of a times x minus a. And what I want to point out is that this equation and this equation are literally the same thing. Linearization of a function at a point is the same as finding the equation of the tangent line at that point. Right? You're making it linear. You're finding the equation of the line. And the idea, if you recall, is that we are using, or we can use this linearization to estimate the value of a function in a place that might be challenging. So let me show you a quick example. Let's say I want to estimate, let's say, the square root of 10 by using a linearization of, say, f of x equal to the square root of x at a equal to 9. Or in less fancy words, find the equation of the tangent line at the point and then estimate the value of the function at the point 10. Let me draw a picture. I feel like I didn't say that very well. So what I'm saying is, here's my square root function. Maybe here's x equal to 9, and the corresponding y value is 3. And the idea is that we are going to then find the equation of the tangent line. And then we're going to plug in 10, which I'm going to say is way over here. We're going to plug in 10 and say, well, the function value, which is whatever that y value is, and I know, sorry, let me make this a little bit more dramatic. Sorry, let me go to the other side here. If I'm looking at the screen like, you guys can't see the difference between those two points. I can't see it. So, right, again, the idea here is you've got this function. And maybe say like, this is the point 9, 3. And the idea here is that we're using the tangent line at that point. Right, that's your linearization. Say, well, if I plug in 10, instead of finding the y value there, which would be the square root of 10, right? So that there, that's the point 10 comma square root of 10, whatever that is. We're going to go up just a little bit higher on the line and say, oh, that's the point 10 comma L of 10. And what we're going to see is that the square root of 10 can be very easily approximated by L of 10. So that's the whole idea. You're using the linearization to approximate a value of a function that's not easy to actually calculate. And in this particular case, here's the calculation, right? We know that our function is x to the 1/2. The derivative is 1/2 x to the negative 1/2. The nice value that we're plugging in is 9, right? We're using that point. Our point is 9 comma 3. So that's our x and y coordinate. And then we find the slope. So the slope is going to be f prime at 9, which is 1/2 times 9 to the negative 1/2. Let's see, that's 1/2 times 9 to the negative 1/2 is 3 to the negative 1, which is 1/3. So the slope of our tangent line there is 1/6. So our linearization is our y value, our f of a, which is 3, plus our slope times x minus our x value, which is 9. Or again, if you prefer, right, it's y minus 3 equals your slope times x minus 9. We're just bringing the 3 over and then calling y L of x. And then you can plug in 10, say, oh, the square root of 10 is approximately L of 10, which is 3 plus 1/6 times 10 minus 9, which is 3 plus 1/6, which is a number. It's 3.1666 forever. Or 19.6. Okay, but now the idea is we're extending this to surfaces. So instead of having a curve and finding the tangent line, we're going to have a surface and find the tangent plane. I'm not great at drawing this. I know, and Professor Lewis definitely had some, in fact, I think I have his notes up. I imagine he showed you guys this in class already. So I don't really need to show you again, but just in case you didn't see it, right? The idea is, let me share my screen for one brief moment. You might have some surface like this, and the idea is that we're going to find, actually, we're going to find tangent lines in the X and the Y direction. And then, I mean, so the process is not super complicated, but the idea actually is a little complicated. The idea is that you find this tangent line, you find that tangent line, and then you find the equation of the plane that has both of those two lines in it. I don't know why he's finding the spread one, to be perfectly honest, because his notes aren't filled in. But then we go down, like, oh yeah, you're getting the plane with those two tangent lines in that plane, which is conceptually maybe a bit challenging to think of, like, how do you do that? But the nice thing is that the actual calculation is super straightforward and almost exactly the same as what we've done here. You're just kind of adding in another part. So here's how to write the equation of the tangent plane. So tangent plane equation. And here's, yeah, I mean, do I want to, oh gosh, that's so gross looking, but I guess we'll write it this way. So here's the equation of a tangent plane, plane equation. So our surface is z equal to f of x comma y at the point x naught, y naught. So again, the way you find the equation of the tangent plane is just like we found the equation of the tangent line. It's z minus the z value equal to the derivative, right? Z minus z value equal to the derivative times your point minus the, right, your x minus the x, right? But we have two derivatives now. So it's going to be, and I'm going to write it, no, I'm going to write it nice, but okay. It's going to be z minus z naught, and then you're going to have the derivative, the partial with respect to x, evaluated at x naught, y naught, times x minus x naught. And then you also have to do it for the y's. You're going to have the partial with respect to y evaluated at your point times x minus x naught. Sorry, y minus y naught. Whew. Apologies. And then the linearization, the idea is exactly the same. You want to find the linearization. You're just solving this for z. So it's going to be z naught, which is your f of x naught, y naught, right? It's the point you get when you plug in, right? Now let me actually point this out. If you plug in x naught for x and y naught for y, this is 0 and this is 0. And if z minus z naught equals 0, z has to equal z naught. So f of x naught, y naught is equal to z naught. This is going to be f of x naught comma y naught plus all this garbage we just wrote. The partial of x naught, y, partial at x naught, y naught times x minus x naught, plus the partial, oops, I made a little mistake there, that should be fy, not fx. Basically, it should be each partial evaluated at the point times that same variable minus the actual coordinate of that variable. Same deal here, partial evaluated at the point times that variable minus the coordinate of that variable. It's just a lot to say. So it's kind of it's a bit messy, but if you can connect it back to what we did before, it's not really anything extra to remember. So I know I've only got a few minutes here. I might go a little past, whoops, not past, but like I might be closer to like 150, because I feel like I should give you guys one example here with actual numbers. Again, the nice thing about this is it's not actually that hard to do. So let's find the linearization of the function f of xy equal to, what have we got here? X cubed y to the fourth at the point 1, comma 2. 1, comma 2, 2, comma 1. Okay. So we need to find the partials, and we need to find f of xy. So we need f of 2, comma 1 is going to be 2 cubed times 1 to the 4th, which is going to be 8. And then fx is 3x squared times y to the 4th. So fx evaluated at our point is going to be 3 times 2 squared times 1 to the 4th, which is 12. Fy is x cubed times 4y cubed. And evaluating fy at our point, we get 2 cubed times 4 times 1 cubed, which is 32. And now we have all the information we need to write the equation. Our linearization is f of x naught y naught. That's going to be 8 plus fx, which is 12, times x minus x naught, which is 2, plus fy times y minus y naught, which is 1. That's the whole thing. And just let me say it right. So this here, this is our f of x naught y naught. This is our fx evaluated at x naught y naught. There's your x naught. There's your fy evaluated at x naught y naught. There's your y naught. There's the whole formula. And so here's the idea. Then you can use this formula to say, well, I know what the function is at 2, comma 1. I really like to approximate f of, say, I don't know, okay, 2.2, comma 0.9. Which is not really easy. Like if you actually plug those numbers in here, I mean, sure, with a calculator, it's super easy. But if you actually try to calculate, 2.2 cubed times 0.9 to the 4th, it's kind of a gnarly calculation. But we can get a pretty good approximation, right? If we actually plug this into this thing here, we're going to get, let's see, it's going to be approximately L of 2.2, 0.9, or the linearization at that point, which is going to be 8 plus 12 times 2.2 minus 2 is 0.2 plus 32 times 0.9 minus 1 is negative 0.1. So we end up with 8 plus 12 times 0.2 is 2.4. 32 times negative 0.1 is minus 3.2. So it's 8 plus 2.4 is 10.4. Minus 3.2 is going to be 7.2. Whereas if you actually plug that in, you do get a value that's actually very, very close. The first 2 decimal points are the same. Let me check one thing. I just want to see 2.2 to the 3rd is 10.648 times 0.9 cubed. Sorry, 0.9 to the 4th. That doesn't seem right. Oh, I feel like so maybe the person doing this actually didn't do the work. That's also perfectly okay. 4th, yeah. Sorry, one second. Yeah, so if you actually use a calculator, you get 6.986. So not a bad estimate. I mean, not perfect, obviously, but decent.